Alright, hello. So what we're looking at in this video is a new topic, continuing where we left off talking about limits. Now we want to look at something called continuity. And so this first video we're just going to get an introduction and some of the basic laws. Oops. Oh, there we go. Okay. Kind of a formal description. We say a function f is continuous at a, so this means we're talking about continuous at a point. If the limit of f of x as x approaches a equals f of a. So you may remember when we're talking about limits, in general, we can't assume that this is true. The limit is in no way automatically assumed to be equal to the function value. But if it is, it means that the function was continuous at that point. So nice property to have for limits, but it's the defining property for continuity. So that's at a point, and then we say a function is continuous on an interval if it's continuous at every point in that interval, or every number, as it may be for us, in that interval. So got an extra note here. Informally, we can think it's continuous if you can draw the graph without lifting a pen from the paper. So you just have a crude graph here, something like if I can sketch the whole thing, and if I had to jump down to there, well then that wouldn't be continuous, because I had to jump when I was drawing it. Okay? So if you don't have to do that, if you can trace the whole thing out informally, that's how you can think of a function as being continuous on an interval. Okay, so if it's not continuous, then we say it has a discontinuity at that point. We've got some graphs below that illustrate different types of discontinuities we may encounter. Removable, there's an example. We've got that point. It's almost like you picked it off the graph and moved it. We've got a jump discontinuity, kind of like the one I just sketched on the previous slide. We've got an infinite discontinuity. That would come about from infinite limits, if you think about what we did earlier. And then a oscillatory, kind of a weird one. It doesn't always get brought up, but I wanted to mention it. Type of discontinuity. We saw that with some limit stuff as well. So these are kind of getting more complicated as we move across. But those are some of the types of discontinuities that we typically encounter. Honestly, we don't run into the oscillatory one too often. So our definition involved limits, or we never say, but it's two-sided limit, left and right. We also have this idea of, or notion of one-sided continuity. So we've got continuous from the right if that defining relationship there, we've got it for that right-hand limit. And continuous from the left if, likewise, that defining relationship where the limit equals the function value, but just the one-sided limit. It's a very natural definition there. So here's an example. Between -1 and 1, so this is that open interval. So don't get confused, it's not the point, -1, 1, it's the interval. From -1 to 1, the arcsine function or inverse sine function is continuous, and we say it's continuous at the endpoints as well, but it would only be one-sided continuity because there's nothing from the right here and there's nothing from the left there. So one-sided at those endpoints. Okay, so most of the functions that it turns out we end up encountering, at least in this course, they are continuous on their domain, so where they're defined. That includes polynomial functions, rational functions. We saw that before when we talked about limits because we said that the limit equals the function value. We hadn't mentioned continuity yet, but that's exactly how we define continuity. And even more than that, root functions, trig functions, inverse trig functions, exponential, logarithmic functions, all of these. So you could think of some examples. A root function maybe generically looks something kind of like this. Here's an example. Trig function, where it's defined, maybe it's a oops, not a very great one there. Let me not try to draw a tangent or something similar, so let me just say certainly something like this, maybe cosine looks like there, an approximation. An exponential function, maybe it's a base between 0 and 1, so it looks like this. Something like that. Logarithmic functions, maybe something like that. So, not defined everywhere necessarily. Logarithmic functions, for example, would only be defined for positive real numbers, but where it's defined, it is continuous. So that gives us really a huge amount of functions, and basically all the functions we typically work with. Well, these would be isolated. When you look at the next thing we want to mention, laws of continuity. Not an official thing, so I have it in quotes there. But keeping all those functions that we said were continuous in mind, now when you throw in all these arithmetic operations to create new functions, so if I add two functions that are continuous, well, then it's continuous at that point. And, addition, subtraction, multiplication by a scalar, multiplication of two functions, division, provided you don't get division by 0. It always results in a continuous function. Now, if you were in a course where you kind of study and prove these things, you go in greater depth, and you do that in a course called analysis or real analysis, something like that. And there are proofs that you can find in the appendix for the book we're using, but we're just going to believe it, and it hopefully kind of makes sense. So, a quick example, something like this. You could have a function like k of x equals 2 to the x minus cosine of x. Right? Let's say plus, strictly speaking, but whatever. So we said exponential functions are continuous. We said trig functions are continuous on their domains. And so the sum of two of those continuous functions would be continuous. This is kind of like some of the limit laws. We don't formally sit down and think about it. You just kind of have internalized it, and you just know that that makes sense. So it's nice behavior. It is continuous. If we don't specify a point or an interval and we just say is continuous, we mean continuous on the largest set for which it's defined. Another operation that we have with functions that we don't have with numbers, it's a trickier one, is composition. And so if, again, you can kind of, one way to think about this is kind of a machine process where it's going through two machines back to back. However you want to think about it, it's kind of maybe a little bit silly, but maybe how you first think about it. But if G is continuous at the point A and F is continuous at G of A, then F composed with G is continuous at A. So that's a continuity law to remember. And just as kind of a side note, I wanted to mention, this is an important one. It's proved using a limit law. We're not going to go through the proof, but this says that if F is continuous at B and the limit of G of X as X approaches A is B, then the limit of F composed with G of X as X approaches A is F of B. And if you like, there's kind of maybe an in-between here. You could say this is F of that limit, and then go to that equality there, maybe if you like. But this step here is entirely because of F being continuous at B. All right, so and that's something that gets revisited in Calc 2 and even in multivariable calculus. This is the continuity law, so to speak, but this important rule is floating in the background. Okay, so real quick to wrap it up with a quick example. It's asking us to explain why this function p of t is inverse cosine or arc cosine of 3 minus t over 2, why that's continuous on its domain, and then state the domain. So as to the y, we could say 3 minus t over 2 is a polynomial. And so it's continuous everywhere. And inverse cosine is an inverse trig. And that's continuous on its domain, which is from -1 to 1. And so the composition is continuous. And that composition is just exactly that function. So where is it continuous? What's the domain? Well, from what we mentioned here, we know that the inputs for the inverse cosine function have to be between -1 and 1. So looking at this as an input, we could say we're going to require 3 minus t over 2 to be between -1 and 1. So that means 3 minus t has to be between -2 and 2. And I'm a little tight for space here, so you got to forgive the organization. I'm going to subtract 3, let's say -5 less than or equal to -t less than or equal to -1. And then I can multiply everything by -1, flips the inequalities, and I end up with 1 less than or equal to t less than or equal to 5. So that is my domain down there. Alright, so anything for t between 1 and 5, this is between -1 and 1, and that's where that function is defined, that's where p is defined, and so that's where it's continuous. Alright, so we start out defining continuity at a point, and then on an interval. We mentioned discontinuities, had a few examples of the types we could see. We mentioned the one-sided continuity, and then we looked at the laws, and finishing up here with an example where we're using what we know about polynomials, inverse trig functions, and then that last property where it says it tells us a composition of continuous functions is continuous.